Hello everyone, my name is Ned Dimitrov and I'm an assistant professor in the Operations Research Department at the Naval Postgraduate School. And today I'll tell you about some joint work with Valentin Jordanov, my co-author who works for Yantel LLC. Today I'll tell you about probability density function transformation using seated localized averaging. So let me just set up the problem background a little bit before we get into the details. So different radioactive materials and their associated decay chains produce different energy spectra. And so it's natural that people try to identify the material from the energy spectrum created. So on the left-hand side here, you see the energy spectrum produced by an americium-241 source as recorded by a sodium iodide scintillator. But in particular, one of the things that happens when you collect these energy spectra is that you get these kinds of Gaussian-looking peaks. And the wideness of this peak is basically determined by the noise in the scintillator and also the noise or the random process of the radiation getting to the scintillator. And so what we would really like is sharper peaks because they help us identify the material more exactly. So we would like to start with a spectrum like this on the left and get a spectrum like this on the right. So the spectrum on the right was produced using seated localized averaging. And in particular, you should notice that these peaks here are a lot sharper than the peaks on the left. So we'd like to start with a noisy spectrum and somehow denoise it. That'll help us identify the material more easily. So there are a number of methods in the literature for doing such post-processing of the spectrum. So in particular, the main methods are what's called spectral deconvolution methods. And these work basically by modeling the input to the detector as a sum of the produced energy spectrum plus noise from the instrument, both of which are random variables. And then this instrument is actually getting the sum of those two random variables. And so the idea is to try to somehow deconvolve or back out what the values of each of the random variables was. But the problem with these methods is that they're computationally intensive. They require a lot of custom data for a particular source, for a particular instrument. And there's an excellent paper in 2000 that summarizes and compares some of these spectral deconvolution methods. Today I'll tell you about another method of post-processing the energy spectrum that's called seated localized averaging, or SLA. And the basic idea behind seated localized averaging is that we're going to average multiple pulse heights recorded by the detector to remove noise from the spectrum. And the basic benefit of SLA is that it's a real-time process. It's not computationally intensive. You can do it in real time, and you can implement it in hardware. So let's see what the basic idea behind seated localized averaging is. So we begin with the idea that we want to average multiple pulse heights. So the first thing we might think of is averaging everything. So that means averaging any pulse height that we get, regardless of which energy channel the pulse height shows up in. But if we do that for this particular energy spectrum, an energy spectrum that just has two peaks, then what we're going to get as an average is just a delta function and the mean here, right at 0. And so that's not very useful to us because we got rid of both of the peaks and we introduced an artifact that's right in the middle over here. And so averaging across everything doesn't work because we get distortion. So the next idea one might try is averaging across small windows. So here we've split up the channels into small windows and we're just going to average events that fall inside of each window. But if we do that, then for each window we're just going to get a single value, and so that takes this original spectrum and turns it into a step function, and that's also not very useful. And so the basic idea of seated localized averaging is that we're going to average across a dynamically moving window. So let's see how exactly seated localized averaging works. So imagine that in this horizontal line right here, we have all of the channels that can be detected by the detector. And suppose that this red dot is the first pulse height that we measured. When we measure that pulse height, we're going to place an averaging window around that pulse height, represented here by this blue line. Next, if we detect a pulse height that's outside our averaging window, we're just going to ignore it, so it has no effect. But if we detect a pulse height that's inside of the averaging window, then we're going to take these two pulse heights and we're going to average them. And very importantly, we're going to move the window so that it's centered at the average of the two pulse heights. So we've recentered this averaging window, and we can continue the process from here. So we can wait for a third pulse height to fall inside of the window, then average the three pulse heights together and move the window again to the center of the three. And so there are two key parameters to defining the SLA process. The first is the half width of the averaging window. That's basically how big this blue line is. And the second is the number of pulse heights to average before we output something. So in this particular example, we've chosen to average just 2 pulse heights. And so after we get the second one, we're just going to output the center of the averaging window as a reading from the detector. So let me tell you a little bit about how one could implement SLA in hardware. So let me tell you how to read these graphs. So on the left side here, we have just the channel number of the detected pulse height. On the right-hand side, we have the spectrum memory, which basically says what the output spectrum is going to look like. And in the middle, we have an area of memory called averaging memory that basically performs the SLA transformation. So imagine that the first pulse height that we measure comes here at channel number 996. And when that pulse height comes in, we're going to look to see if there are any averaging windows that are close to that pulse height that we need to average the pulse height with. But there aren't any in this particular case. And so we're going to start a new averaging window. So since they were all zeros, that means there were no averaging windows here. And so we're going to start one by putting in the pulse height that we measured and a count of how many pulse heights, which is just 1 so far. Suppose now that we measure a second pulse height that comes in at 999. Now this pulse height does have an averaging window that's close to it. And so we're going to average 999 and 996, or sum them currently. So we're going to sum them and move the answer to the center where the average would be, and we increase the count by 1. So now there are 2 pulse heights that are in there. If we get a third pulse height, maybe it's off to the side here, so it has no averaging windows, so it starts a new averaging window. Maybe we look at our fourth pulse height, it comes in here, so we have to average it with this averaging window, and we increment the count by 1 again. And suppose that for this particular example, we've chosen to average 4 pulse heights. So once this fourth pulse height comes into this averaging window, instead of just incrementing the count by 1, here we set everything to 0, and we actually output a single count into the spectrum memory. So this is what the post-process spectrum is going to look like. So that's how one could implement SLA in hardware. But what are the properties of SLA? What does it actually do to the energy spectrum? SLA has existed for a number of years, and there's a lot of practical experiments using it, but the purpose of today's talk is really to give some of the theoretical background behind this process. So to model the properties of SLA, we're going to have the following probabilistic model. Imagine that the energy spectrum gives a probability density function. So the spectrum that we saw at the beginning is just giving us a PDF of a random variable, meaning that the pulse heights that we get at the detector just come from this probability density function. So the first pulse height that we measure is a random variable with a PDF equal to that energy spectrum. The second pulse height that we measure that falls within the averaging window is similar to the first, but its PDF is restricted to be inside of the averaging window because we know for a fact that it fell inside of the averaging window. And the output of the SLA process, if we're averaging just 2 pulse heights, is going to be this first random variable plus the second one over 2. So that's the output of SLA P0. And so to analyze the properties of SLA, what we're going to do is we're going to compare the original PDF for f of x with the output PDF for this random variable P0, that's the output of SLA. So what are some of the theoretical properties one might want from SLA? The first question to ask is, what exactly does the SLA transformation do? In other words, can we characterize the output of the SLA transformation? And we can do that with the following lemma. In particular, we have an exact characterization of the output PDF in terms of the input PDF. And you can see here that it's not too bad of an integral. where the input PDF appears and also the input CDF appears. And so using this formula, you can explicitly see for a particular input PDF what the output of the SLA transformation would be. The second question that we might have is, does SLA shift the peak locations? And this is a property that we wouldn't want to have. So we would like the peaks to remain centered where they are, because that's going to help us identify the material. And we can do that with this second lemma, which says that if the input PDF is symmetric about mu, then the output PDF is also symmetric about mu. And what this means is that if the input PDF is symmetric with a mean mu, then the output PDF is also symmetric with the same mean mu. Interpreting this, it means that if we have a single peak, the SLA transformation does not actually shift the peak location. The second question that we might ask is, does the SLA transformation actually make peaks sharper? In other words, does it reduce the full width half max of the spectrum peaks? And we can answer this question with the following lemma, that if the original input PDF is symmetric and increasing towards the mean, this means that it looks like a single peak, then the output random variable has a smaller variance than the input random variable. This means that the peak is actually getting sharper. So to summarize these theoretical results, for things that look like a single peak, in other words, they're symmetric and they're increasing towards the mean, SLA has the following properties. It maintains symmetry, it maintains the mean, and it reduces variance. In other words, it sharpens the peak. And the basic idea is that for things that have multiple peaks, if we pick the averaging window to be small enough, then those spectra are going to behave as though they have a single peak locally. So let's see some examples of the SLA transformation. So in this example, on the horizontal axis we have channel number, on the vertical axis we have frequency, and suppose that we have just a simple Gaussian standard normal PDF. So that's in this black line right here. And with the various red lines, we're representing the SLA transformation, where we fix the number of pulse heights to average to 2, and we're just changing the parameter that says how big the averaging window is. So that's this radius parameter r. So as the radius parameter goes to infinity, it means that we're basically going to be averaging 2 independent standard normals. And that gives us another standard normal with a smaller variance. And that's exactly what we see with a very high r right here. And as we make r to be smaller and smaller, we get something that's closer and closer to the original PDF. So in other words, as the averaging window gets smaller and smaller, you get a smaller and smaller transformation of the original PDF. But all of our theoretical results are holding out here. The original distribution is a single peak increasing towards the mean, and the resulting distribution maintains the location and sharpens the peak. So in this picture, in the light blue, you can see some simulated SLA results of a transformation, and in the red line represents the theoretical output that we should be getting from the lemma that characterizes the SLA output. And you can see that there is excellent agreement between these two. In this graph, on the bottom axis, we're presenting the SLA parameter that specifies the window length again, changing it from 0 to a very big number, like 5. And on the vertical axis, we're seeing the variance of the output distribution. So this is again for just a single Gaussian peak. And you can see that when r is very small, the variance of the output distribution is the same as the variance of the input distribution, around 1. And as r gets bigger and bigger, the variance gets smaller and smaller. And it's flattening out to about a half, which is the theoretical upper bound when we're averaging exactly 2 pulse heights. Of course, you can get this to be smaller if you're averaging more than 2 pulse heights. So let's see what SLA does to some non-single peak distributions. In this particular graph, we have the uniform distribution represented by this black flat line here. And in the 4 red lines, we're seeing the SLA output for various values of the averaging window parameter r. As the averaging window is big, maybe around 1, we're just averaging 2 independent uniforms, and that's why we get this standard triangular shape. And for smaller values of r, you get these bathtub-like shapes from the SLA transformation. And just to double check our work again, Here's, again, a simulated output from SLA versus a theoretical output, and you can see that there's excellent agreement between the two. So let's see what SLA does for a distribution with multiple peaks. So take this distribution that's just a mixture of two Gaussians. When we have the averaging window R be very large, we'll be averaging across these two peaks. And that's why for these large values of R, we're getting this artifact in the middle right here. That's the mean of the two peaks. But as R is getting very small, around 1, you can see that this distribution is now acting as though it has a single peak locally. And so both of the peaks are getting sharper, and the dip between the two peaks is getting smaller. So both of them got sharper due to the SLA transformation. And that's the basic idea here. For multiple peaks, if the averaging window is small enough, they act as though they're a single peak. And that brings me to the conclusions of today's talk. SLA, which I've presented today, presents a real-time method for decreasing instrument noise when acquiring radiation spectra, and it also has provable theoretical properties. The main drawbacks of SLA are first that it reduces the number of detected events. In particular, since, for example, we might be averaging 2 pulse heights to output a single reading on the spectrum, that's the kind of reduction in the number of events that we would get, a factor of 2. But there are some ways that one could get around this. And the second drawback is that those other methods that I mentioned at the beginning of the talk, the spectral deconvolution methods, even though they're computationally expensive, they may be more accurate because you could input a particular model for a particular instrument for the specific noise that you get out of that instrument to help you do the deconvolution. And so SLA has its advantages and its drawbacks. And SLA was patented by my co-author in 2007. So thank you very much for listening.